All right, let's get this going. Time for problems, what is it, 5 through 8? Okay. How'd that get there? Oh, there they are. There's problems 5 through 8. I mean 4 through 8. Okay, well anyway, number 4. So the way the question is given to you, they give you a function for the force, and then they're asking for the work done. Well, all right, you should be savvy now to the fact that work is the integral of force. So that means that we just need to integrate that function right there. And so using what we know about power rule, we're going to add 1 to each of the exponents, and then divide by the new exponents. All right, and that will give us a force function. All right, now I'm trying to emphasize the fact that it's a force function because for some reason, selecting that answer, which is answer choice D, is not right, and they're not considering it as correct. So, I'm sorry, work function, not force. They gave us force, so this is work. All right, so why isn't that the right answer? Well, because they asked for the work done as the object is moved from 0 to D. So in other words, they're setting you up for a definite integral. Right? Really what they were doing is, what's the integral of this from 0 to D? All right, so they could have done it from anywhere to anywhere else, right? They could have been like from D over 2 to D, or from D to 2D, and then you would have different bounds to plug in. All right, so 0 to D, though, is a nice and easy set of bounds, right? If we plug in D, we just get the same thing back with a D instead of an X. B, D, gosh, all right. And then minus 0, because if you plug in 0 for X, you're just going to get 0 back out, and so there. That is the answer with D's instead of X's. So it has to do with the fact that they gave you a specific range over which work was done. All right, next one. Force is proportional to velocity, they say, for towing this barge. In other words, they're cluing you in that it's a, what kind of a force is that maybe that I've seen before? Hint, it's dragging the barge through the water. Oh, a drag force. Yes, that would be it. Which, anytime you move anything through any kind of a fluid, you're going to get a drag force. So towing through water or moving something through the air, either way, there is a drag force involved. All right, so for this particular case, they tell you 3,000 watts at 3 kilometers per hour, and then, oh my gosh, what is the power at 9 kilometers per hour? So this doesn't seem like any kind of a drag force that you've done before. And so you might be thinking, do I have to use integration? Like, how do I get it to be drag? And actually, you don't. There is a formula for power that relates to force and velocity. And you might remember it as it's in fact force times velocity. All right, so, and that works for any situation, right? If you want to move something at a constant speed against a certain opposing force, then it takes a certain amount of power to do it. So examples we've used of this before are like pushing something across the floor, right? You've got a friction force that opposes you. So if you want to move it at a constant speed of whatever, you have to put in that force, right, to keep it going at whatever same speed you're going for. All right. So the weird thing in this case is that the force is proportional to the velocity. So it's something like kV for your force, and then V. All right, so that means that the power used is something like kV squared. All right, now I'm not going to get all like algebra technical here and figure out, all right, what is K and all that kind of thing. We're just going to go with, look, if at 3 kilometers per hour it uses 3,000 watts, and 9 kilometers is 3 times as fast. If the power depends on the square of the velocity, that means that if I triple the velocity, the power use is going to be 3 squared of whatever it was before. All right, so if it took 3,000 watts at 3 kilometers per hour, I triple the velocity. Now that means we're going to take 9 times the power, 3 squared. All right, and 9 times 3,000 watts is 27,000 watts. So 27 kilowatts. All right, if they had merely, say, like doubled the speed to 6 kilometers per hour, then it would have just been 4 times the power, so 12,000. All right, fine. So understanding that that the power depends on the square of the velocity because the force is a drag force that you are opposing was the key to working out this question. All right, next one. If the position is this, right, t to the 3/2 power, and they want to know the kinetic energy, or rather, what is the kinetic energy proportional to? Well, kinetic energy is related to velocity, or speed. So that means we need a function for speed. That would be the derivative of this one. So v is 3/2 t to the 1/2. Okay, so then I can go over here and plug that into kinetic energy is 1/2 mv squared and oh no, I don't have the mass. It's okay, guys. The reason it's okay that we don't know the mass and then like this 3/2 constant seems to figure nowhere in there at all is that it's just asking what is the kinetic energy proportional to. Not what is it, but what is it proportional to in terms of the time. So that means that all we really care about is the time part of this. So what we got was the velocity depends on time to the 1/2 power. So if kinetic energy depends upon v squared, that means that the kinetic energy is proportional to, that's what this squiggle means, it's a technical symbol for proportional to, well, t to the 1/2 squared would be t to the 1st. All right, so that's where that comes from. Next one, number 7. So we've got this rock, and we're lifting it up with some force that is larger than its weight. Confusingly in my explanation here, they have the symbol W not representing work, but rather the weight of the object. So they're going to talk about the work done by, or they don't explicitly say this, but we're going to talk about the work done by the applied force, and then also the work done by the weight of the object. Okay. Now, you may be thinking, what do you mean the work done by the weight of the object? Like, when have we talked about work done by weight? Well, gravity is a force, and when gravity does work, since gravity is a conservative force, we don't usually talk about the work done by it. We will more frequently just talk about the change in gravitational potential energy. Because when you have a conservative force doing work, the work that it does is going to equal the opposite of the change in its gravitational potential energy. All right. Also, so I think that's good enough there. We can say the work done by gravity, done by the weight of the object, is equal to the opposite of the change in its gravitational potential energy. Okay. Now, they want to know what is the change in the kinetic energy of the object, given that the force that's being applied here is larger than the weight of the object. Okay, so that means that if I were going to write this out sort of explicitly, we would say final minus initial equals work. All right, the initial energy is, well, let's presume nothing. All right, we can say that it's initially at rest. I'm good with that. And the final energy would be, well, if this force that we're lifting it with is greater than its weight, then that means that it must end up with some amount of kinetic energy. Because if the force we were applying were merely basically its weight, okay, then we'd just be talking about really lifting the object, right? So I realize that during its motion it will be moving and therefore have some amount of kinetic energy, but in terms of work energy theorem, if all you do is you lift an object like this, right? There, I took it from the ground to up here, right? This, whatever this is I'm holding that's imaginary, the work done is just going to equal the change in gravitational potential energy because I basically just overcame its weight. I'm applying a force equal to its weight. As long as I'm, say, lifting it at a constant speed, I'm not also changing the kinetic energy as I am moving it. All right, now this force is greater than the weight. So that means that it will end up with kinetic energy and gravitational potential energy. All right, and then the work being done is going to be force times the distance over which it's applied, assuming that the force is a constant force. Okay, so that means that the change in kinetic energy, all right, I mean, we started with presumably 0 kinetic energy. It wouldn't have to have started from rest, but we're going with it. The change in kinetic energy is whatever the final is if the initial was 0. And that equals force times distance minus the increase in gravitational potential energy. All right. Well, at this point, you might be looking at that and being like, this doesn't look like any of the things that I'm seeing here. Which option is correct? All right, well, let's express gravitational potential energy in a slightly different manner, okay? Gravitational potential energy could be given as mgh, or it could also be given as weight, which is mg, times h. Also, in this case, d, the distance we lifted it, equals h. All right, so therefore, we have Fd minus Wd, right? That's mgh, d is h. All right, so that means that the change in the kinetic energy is, if we sort of factor out the d, that right there. All right, if you like, you could say F minus W is the net force. All right, so that looks like option A. The change in the kinetic energy is the work done by the net force, F minus W. All right, this last question for this video, anyway, number 8. They're asking for the force and then also the direction. So this is one of those areas where the AP is going to just needle you with the sign, okay? The idea is that force is the negative derivative of potential energy. All right, so a lot of the times people will just take a potential energy formula, they'll take a derivative and be like, oh, it's 12x minus 4. I am so good at physics. And good, they knew to take a derivative, all right? And then they'll just be like, F equals that. Almost. That would give me perhaps the, well, it's not even really the magnitude of the force exactly, but it's related to what the force is. But the trouble is that this is actually going to give me the wrong direction for things, okay? The force, being the negative derivative of position, is the negative derivative because the sign relates to the direction of the force. So if I were plugging in, say, x equals 0, I would get that the force was 4 newtons to the right, because that would be the positive direction, presumably. But they want to know the force at x equals 3. So that is going to give me, if I plug in 3 there, negative 32. That means that it's 32 newtons in the negative x direction. All right, so the direction of this force and also its magnitude changes with position. That's what this is saying. All right, a graph of this thing presumably looks something like that. Okay, so initially the force is in the positive direction, but a little while later the force is in the negative direction. Also popular, what is the equilibrium position? That would be where the force equals 0, you could solve that equation by setting it equal to 0.